Okay, last time I said you were ready for the formal derivation. Not quite. Let's use these collisions with these carts here. Carts of the same mass. We're going to use these collisions to give us some truly deep insight. Very cool. We're going to combine energy and momentum. You might say, well, what's the difference? Momentum's mv. Energy, kinetic energy is 1/2 mv squared, except 1/2 m speed squared versus m times velocity. So there's some deep insight here. What's the key? Okay, let's get at this. There's the difference between p, which is a vector, momentum, and k, in fact any energy, which is a scalar. We'll say that again. There's a difference between the bulk macro motion of things and the atomic or micro motion, the jiggling that we'll talk about. And this is really cool. It leads to thermodynamics. We'll talk about it in a second. So the role of jiggling energy is a hint at the essence of thermodynamics. So you get a little taste and you get into that in a later course. So let's do this, all right? Okay, so we've got some special cases here that we're going to use to pull this out inside out. We've got two objects coming in. They've got the same mass, so just call it m. No sense calling it ma and mb if they're the same. They're approaching at the same speed, not direction. Okay, so here I've got the JB for just before. Something happens during, and the beauty of momentum and energy is often, especially during conservation, we look at just before, look just after, ignore the messy collision, right? So we've got during the collision, and then we've got just after what's going on. So let's see what happens. In this case, let's first do the elastic collision. That would be with the magnetic carts. You remember they didn't touch. And then we'll do the perfectly inelastic, and that's the case where we got Velcro on here and they stuck together. Okay, let's explore the difference. So the math is easy, that's nice. Get used to setting it up. Momentum, remember you need an x component and a y component. However, in this case it's one-dimensional, so you get to ignore the y. But in general, you just need to do x as though y didn't exist. You need the angles, cosine, sine, and then do the y as though the x didn't exist. And then we've got kinetic energy because it's just before and just after, so again, the height isn't changing much and there isn't much time for friction to come into play. On the surfaces, that is. So let's take a look at this. Here we got two objects coming in, same speed. What's the momentum just before? Well, I got mv, and I've got mv in the negative direction. Since momentum's a vector, I've got to specify the direction with a plus or minus. So I haven't said that, but inherently I'm going to call that the plus direction. All right, good, now we're good. Okay, it's an elastic collision, but I don't even need that. In any collision, if these guys are free to move, not held in place, then you have conservation of momentum. So let's see what's going to happen. Well, wait a minute, what's the total momentum before? That adds up to 0. So the total momentum here is 0. The total momentum after is going to be 0. Now, they could stop, but you saw that they bounced. So the only way that we can get that here is that they go off in opposite direction. Okay. So now I've got the blue one now has a negative momentum, and the green has a positive momentum. Now, in reality, in order to get a 0 momentum, I mean, this could go, 1,000 miles an hour that way, and this is 1,000 miles an hour that way, and the momentum still adds up to 0. We're going to see, however, that this must be the speed v and v. In fact, we kind of proved that last time, so let's talk about this again. So we've got this, it goes in with a certain speed and goes out with a certain speed. Okay, so what have I got here? That means that I've got m negative v plus m positive v, and that of course is 0. Cool. So conservation of momentum satisfied. The key for elastic, though, elastic tells us about kinetic energy. When it's elastic, and we're going to see why this is true, when it's elastic, I start out with 1/2 mv squared, and I end up, and I've got 1/2 mv squared for the green one. When it's elastic, that means that my total kinetic energy stays the same. And so let's see if that's true in this case. 1/2 mv squared plus 1/2 mv squared. And the thing that's interesting to note here again is that I add up the kinetic energies. Just because they're going different ways, it doesn't matter. Kinetic energy is positive. Momentum, one is negative, the other is positive. But here, they don't subtract, they add, right? Energies add up. There's a total, there's more energy, more ability to hurt you, more ability to change you, heal you, whatever it is. So we've got, if that was the only one moving, we'd have 1 F mv squared, 1 F mv squared, atom, cool. And then afterwards, doesn't matter the direction. So yes, it is conserved. In fact, it's 1/2 plus a half, or 1 mv squared. Okay, cool. So that's an elastic collision, and everything is satisfied. Fine. What happens in a perfectly inelastic collision? Right, well, let's see. I've got these guys coming in at the same speed, opposite direction. I'm going to put the negative in explicitly. We'll just use the v as a speed. And so, same deal, right? Momentum in the x. I got mv plus m negative v, or minus mv, just because of the direction with a minus. It's a collision, and they're free to move, so it doesn't matter what kind of collision it is, momentum is conserved. However, perfectly inelastic means they stick. Right? Elastic means they bounce, but perfectly inelastic means they stick. So these guys are going to stick together with Velcro. Now hold on. That means that they've got to move together. So M and M is stuck together, and you see it's got a chocolate coating here. Anyway, never. So how can I have a zero momentum when they're stuck together? One answer, right? The momentum is zero if the velocity is zero. They've got to stop dead. Okay? So this is very different, where here they came in, they bounced, and they went out with the same velocity. Here they came in, stuck, and so they've got nowhere to go in order to maintain a zero momentum. Again, I don't need the y component, but remember that if they're not linear, then not along the same line, you do. And I've got kinetic energy. Let's explore the kinetic energy. Again, 1 F mv squared plus 1 F mv squared, fine. But wait a minute. Inelastic, bouncing, but hitting, deformation, sound, thermal jiggling, right? Or perfectly inelastic, certainly, mostly, when it sticks. You cannot say that they're equal. In fact, how much energy do I have here? Well, 1/2 times 2m times, obviously, 0. Right? So these are by no means not equal. These are not equal. In fact, the question is, how much did we lose? And that's interesting. Why? I mean, momentum is conserved in both cases, but here I've lost all the energy, all of it. All of that, mv squared total, right? So how do I do that? Okay, so coming over here, and we'll talk about the depth of this. I say, how can I write an equation if I can't say this is equal? You know, don't put equals in there, right? You write this, change in kinetic energy is, by definition, the kinetic energy just after minus the kinetic energy just before. Right? Just write it. And that's for all objects, right? So you can put all if you want, whatever you take, whatever you need. So let's see, just after I've got 0, and just before I've got mv squared, because I got 2/2 mv squared, right? mv squared. So how much did I lose? Negative mv squared. In other words, I lost all of the energy by sticking. Where did it go? Where did it go? You know where it went. Okay, but what's interesting is they stuck, and they created some jiggling, right? And some sound. Maybe there's some crumpling, deformation. But the momentum is still conserved. Why don't we lose momentum? So let's go over here and get the punchline to this guy. All right? Why? Quick review. Newton's third law. You know momentum is a vector. As you've said, direction is given by plus or minus. And momentum, plus or minus, matters. Momentum is conserved in all free collisions. That means they're not held into place. They're free to move, kind of, right? If you count both. If you look at it, that's Newton's third law, right? Newton's third law. So, because equal and opposite forces, right? Newton's second law. Each object will receive a net force from the other one, right? So each object does accelerate. You can see that the blue one did change and the green one did change. if you look at them individually. Or we could say that same thing, Newton's second law, another way, and that is that each one gets a net impulse, which changes its momentum, right? These are just equivalent statements of saying the same thing. So where's the key? We've got elastic collisions, inelastic, bouncing, but hitting and creating sound and thermal and stuff, or perfectly inelastic, namely sticking. This has to do with the way that they interact during the collision, and it tells us about kinetic energy, not momentum. And so here's the key. We're still running? We're good. So kinetic energy, as with all energy, is a scalar. And so the direction does not matter. The plus simply means more than some reference zero, some place you defined as zero amount. And negative is just less than zero. So here it is. In touching collisions, not emotionally moving like a movie, but in touching collisions, when they hit, you get atomic jiggling. I do that, my atoms are jiggling, right? They're going crazy, right? You go like this, the atoms are jiggling. Atoms are jiggling. What does that mean? Well, check this out. The total momentum for jiggling is zero. There's no loss to jiggling. Why? Because what's the momentum here? Zero. What's the momentum here? Zero. Momentum, zero. Momentum, zero. The total is 0, 0, 0. So that doesn't carry any momentum. What's the momentum of the universe? Probably 0, right? Pretty good guess. Whatever goes this way goes that way. Right? Total momentum of the universe, 0. That's good, unless, anyway, we'll get into reference range. But what about jiggling? The energy of jiggling is the kinetic energy of jiggling and the potential energy from the bonds of jiggling. Anyway, there's clearly energy from jiggling, because if you touch something hot, it's going to hurt you, right? So it's got energy. So that's not 0. In other words, the jiggling takes away bulk energy of motion. But the jiggling doesn't do anything to the total momentum, because the jiggling momentum is 0. But there is jiggling energy. Now here's the question that I leave you with to ponder. Can the jiggling motion create a bulk motion? And that's thermodynamics, which we explore that. That's sort of the essence of thermodynamics in some ways. Can jiggling motion be harnessed? Everybody go that way and create a bulk motion. Okay? But this is kind of cool. So that's the difference, right? Momentum and energy are different. And you see it in the jiggling. The total jiggling momentum is 0, but the jiggling energy is not. All right, now we're going to get formal on you and derive the work energy theorem. We're going to do the work kinetic energy theorem in what I call Form 1, and then we'll do the work energy theorem, mechanical, in Form 2, and define work kinetic energy and then potential energy as change of potential energy. Okay, next time.